But all of that stuff, the A and B, does A and B really happen? Or maybe actually you need to change B a little bit, or maybe actually we're not accounting for this. So this is where the uncertainty comes in. And so at the moment, just because you see a simulation like this, don't think we understand how galaxies form. We think we might have a general principle of the sorts of things that need to happen, but we're not there yet, and basically convincing most people, myself included, that we actually understand what is going on. Okay, so that's an important take-home point. But clearly we are, I think, making progress. But can we use simulations like this to inform what we might expect to see in observations, what we actually do see, well, okay, that's not quite what we predict. Where could we be going wrong in the prediction? Let's fine-tune that. Does that work? Oh, that works. Oh, no, that doesn't work. Oh, okay, now we need to change something. That's the process that we're going through right now. As for the future, this is the final slide. And I may have gone on a few minutes too long. I apologize. But we know now, or we don't necessarily know, but because we had an idea of how M33, the Triangulum Galaxy, and Andromeda are moving with respect to each other, we know how Andromeda Galaxy is moving with respect to us. We know its radial velocity. We know it's coming towards us at 120 kilometers per second. Okay? So then we decided hey, let's just see what's going to happen in the future of the local group. So this is what's going to happen in our future. It's seen from the viewpoint of where we are right now. So in other words, the galaxy we live in is about to leave us behind. In reality, it's not going to leave us behind. Okay, so it's a kind of a silly viewpoint to look at it from, but it just helps. So what happens is, Triangulum and Andromeda carry on orbiting each other as they were before. Notice M33 now passes a bit closer, gets a bit more messed up. Meanwhile, the Milky Way galaxy is getting closer and closer. And Triangulum's out there, but it needs to fall back in because it's at that point in its orbit. So it falls back in, but now it starts falling back in and starting to get really messed up. And what I really like about this is that basically, little galaxies have been picked on all the time. However, now when these two big galaxies start messing with each other, the Triangulum Galaxy just goes, sod this, I'm getting out of here. And you'll notice it gets ejected. And it basically doesn't come back. And instead, the two galaxies formerly known as the Milky Way and Andromeda merge with each other. And as they merge, actually, you'll notice the sort of thing that they're producing starts to look more and more with time like a big elliptical galaxy. You remember those big balls of stars I showed you? That's actually how we think elliptical galaxies form. A couple of spiral galaxies crash together, and the end result is something that looks a bit like an elliptical galaxy. At the very end of their Triangulum comes back in, and it may actually be completely swallowed up. So in some respect, I should say that this isn't going to happen for another 5 billion years. So, don't panic, as it were. It might be, I like to think of this as the beginning of a new galaxy, although it is definitely the end of this talk. So thank you very much.
I was doing some Googling regarding cartwheels, and I stumbled on the Cartwheel Galaxy.
Oh, yes.
And I'm wondering where that would be relative to us.
So the Cartwheel Galaxy, it's one of the nearer galaxies to us. Now, I can't remember if it's a case of 7 or 10 times further away than Andromeda is, but it's of order, say, 10 times further away. I can't remember the exact distance, but it's that sort of distance. So it's a nearby galaxy, but it's very hard to see actual individual stars to us. But we can see, obviously, very beautiful pictures of that galaxy.
Okay, over here. I have a question relates to the dark matter that was in the Milky Way galaxy, because one of the things that was done was they looked for the velocity of the stars. They went out further in the disk, and they inferred off that the dark matter because of the way the velocities were moving for those stars.
Yep.
How does the dwarf galaxies factor into all that? Because it really looked like it surrounded the galaxies we were looking at.
Yes, so the dwarf galaxies do surround, and there's a large number of them. It turns out, though, that even the total mass of all of the dwarf galaxies together isn't very large in comparison to the total mass that's in the main part of the galaxy, the main Milky Way galaxy. So the total mass of all of the dwarf galaxies, if you add up the Large Magellanic Cloud and the Small Magellanic Cloud, they're really the two most massive dwarf galaxies. And even they are, 1/100th the mass of the Milky Way. So it doesn't really affect the mass too much in that respect. But I mean, what you've just said is one of the evidence, the rotation curves of galaxies and how stars move around the disk galaxies is one of the main pieces of evidence for dark matter. And sort of the measurements of the dwarf galaxies themselves and how the stars move in the dwarf galaxies is effectively the equivalent measurement, but for these much smaller systems.
I have a question regarding the colliding galaxies.
Yes.
If the Big Bang Theory is correct, we're all expanding and expanding.
Yes.
How do galaxies then all of a sudden go at right angles to
Yep.
this expansion?
Yeah, so no, that's a very good point. So anytime I give this talk, I'm always curious as to whether or not I should explain that a bit more, because you're absolutely correct. In the Big Bang Theory, basically, the initial event, who knows what actually happened, sends all material away from each other, and there is general expansion. However, not all, so the entire universe is indeed growing in size, and that is the expansion of the universe. However, some objects, that expansion has, if you like, a kind of force that's pushing galaxies apart, is sort of a naive way to think about it, okay, or the way I think about it at least. However, for galaxies that are actually quite close to each other, for objects that are quite close to each other, the dominant force need not actually be that expansion, but it's actually just the gravitational attraction. So all of the universe is basically expanding away, but at the same point there's this fight with gravity which wants to pull everything back. Okay? Now it doesn't win out overall, but in small areas of the universe, for example, where two galaxies happen to be quite close to each other, the expansion effect isn't enough to counteract this pulling together because of gravity. And so it's really just that. It's really the gravity is acting very nearby, and the merging is happening for systems which are, in terms of the overall size of the universe, very close to each other. So there the dominant force is actually the inward pull of gravity, which causes the merging, and it's not that outward expansion of the universe, although that is also happening. In fact, one way a colleague of mine has often said that if we truly do live in an expanding universe, then we better get used to observing the local group, because at some point it's going to be the only thing that we can observe, because everything else will have been sort of moved away from us because of the expansion. That's obviously in an incredibly long time. But it's just that point. It's gravity wants to pull in, and for things which are close together in the first place, gravity wins. Overall, it loses.
Yes. With the very small dwarf galaxies, where you can see the stars,
Yes.
are there movements modeled out as the dark matter being more of a point source, or are they embedded in a field of dark matter? And if the latter, how much bigger diameter beyond the stars does the dark matter model out
that's
as?
an absolutely excellent question in an entire field of research. So yes, so the challenge for us is that we believe that there's probably, well, I won't say we believe, I don't like using that term when we're talking about astronomy. We see evidence that there is this thing called dark matter, and it's there. When we look at how all of the stars are moving, what it means is that it's basically they're embedded in what you describe as a field of dark matter. So the dark matter, everywhere where we see stars, there's also dark matter in all of that area. And it may be that the dark matter extends out much, 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 much further than the stars do. The problem, of course, is we can't see the dark matter, so we don't actually know how far out the dark matter goes. But it goes out to at least as far as the stars in all cases, and it may well go out further. Trying to actually trace what is that distribution of dark matter is actually something that's very important in understanding what might dark matter be, because depending upon what particle theorists or whoever think the dark matter particle is, that would predict different things regarding the shapes of the dark matter halos, how dark matter should distribute itself within a galaxy. So it's an excellent question, and at the moment, the dark matter we see out as far as the stars go, and we suppose that it probably goes out further, but since we can only measure things that we see, and we don't see any stars out further, then we can't actually put on any strong constraints.
Okay, so as we absorb or any large galaxy absorbs the dark matter-rich dwarf galaxies, does that mean that our dark matter to observable matter ratio would increase?
Yes. Yep. Absolutely correct. It probably doesn't increase very much anymore because the things that the Milky Way is absorbing as so much less massive than it in the first place that it doesn't have a major effect at the moment anymore on the total mass. But yes, so when you have two galaxies merging together, perhaps not even two dwarf galaxies, the stars merge together, the dark matter merges together and forms a new, bigger dark matter halo. So yes, so the dark matter gets absorbed and basically becomes part of the galaxy, the same as the stars.
Does that in any way bring the dark matter like closer to us, or closer to something that we'll be able to, detect directly?
Not in any obvious way, no.
Okay.